Good morning. This is Vamsi Mohan, Professor, Department of Civil Engineering. In today's session, I will be discussing some examples on closed coils helical springs. So already we have discussed the types of springs. Okay. So the closed coils helical springs are those in which the helix angle is very small. Okay. And the coils are closed spaced very closely. Okay, and we will see the cases of springs subjected to axial load and axial twist. Okay, so first case, axial load. When a closed coiled helical spring is subjected to axial load, what will be the deflection and what will be the strain energy stored in that we'll see. Okay, so here d, small d is the diameter of the coil, diameter of the wire, and capital D is diameter of mean diameter of the coil, and capital R is mean radius of coil. Capital R is the radius of coil as shown here, and number of turns means 1, 2, 3 like this. These are the number of turns. N is represented as number of turns here, and C is modulus of rigidity of the material of the spring. In some books it is used N or G also for modulus of rigidity, and here the axial load is W, and let tau be the maximum shear stress induced in the wire due to twisting. The wire is subjected to twisting. Theta is the angle of twist in the spring wire. Delta is the deflection of the spring. Okay. So this is the notation we used, and delta is, already we have seen this derivation. Delta is 64 W R cube N divided by C D power 4. The notation is already mentioned. Okay, so here the delta, the deflection is given as 64 W R cube N divided by C D power 4, and the strain energy stored in the spring is subjected to some extension or contraction, isn't it? Due to axial loads, it will be subjected to some deformation, extension or contraction. So here the extension of the spring is delta. So the work done on the spring due to the axial load is half into W, average loading into deflection, delta. So this work done on the spring is stored as strain energy. Okay, so the work done is equal to strain energy. Okay, and stiffness of spring is load per unit deflection. The stiffness of the spring is defined as the load per unit deflection. So load is W and deflection is delta. So the stiffness will be W by delta. And from this equation, W by delta is CD power 4 by 64 R cube N. Okay, from this equation, W by delta, the stiffness is given as CD power 4 divided by 64 RQN. Okay? Yeah. These things already we have discussed. Okay? Now let us see some examples now, numerical examples. First one, a closed coiled helical spring is required to carry a load of 150 kilonewtons if the mean coil diameter is to be 8 times that of the wire. Calculate these diameters. Take maximum shear stress as 100 MPa. Okay. So here the torque is given as W into R. Okay. The torque is given as W into R. Torque means the twisting moment. Okay. The twisting moment to which the wire of spring is subjected to is equal to W into R. Okay. Also, the torque is given by this from the torsion equation, where tau is the maximum shear stress. Okay, in the wire of diameter D. Okay, so torque also is given by torsion equation is this one. So now we can equate this to WR is equal to pi by 16 tau dq. Pi by 16 dq is equal to section modulus. Okay, and tau is shear stress. Tau is shear stress. Okay, so the maximum shear stress is given already in the problem. It is given as 100 megapascals. 1 megapascal is 1 Newton per mm square. So tau is 100 Newton per mm square, and axial load W is 150 Newtons. And what else is given is capital D is given as 8 times of small d. Capital D is mean coil diameter. Okay, and small d is wire diameter. So mean coil diameter is given as 8 times that of the wire diameter. So we have to find what are these diameters from the given data. Okay. So how will you find this now? So here you know W and small r, here capital R is given. Capital R is capital D by 2, isn't it? So we can take this as half WD is equal to pi by 16 tau dq. And now capital D can be replaced with small d. Okay, because capital D is given as 8 times the wire diameter. So we can replace this capital D. Okay, so here half W into 8 times small d is equal to pi by 16 into 100 into small dq. Okay, so from this W is known, W is given already. What is the load? 150. So we replace this W here by 150. So you can now find the diameter D from this. Okay, yeah, D square is equal to something you can get. Okay, 4 times. This is 2, this is 3. Okay. So 96 by pi d square. So d will be 96 by pi under root. Okay, which comes out to be 5.53 millimeters, and it is rounded off to 6 millimeters. Okay, the higher value will take next higher number. So taking the wire diameter 6, the coil diameter will be 8 times of that, that is 48 millimeters. The coil diameter will be 48 millimeters. Okay, so like this we can solve the problem. Okay, here we need to remember these expressions. Okay, all these expressions we need to remember. Next, another example. A closely coiled helical spring of round steel wire 5 millimeters in diameter, having 12 complete coils of 50 mm mean diameter, is subjected to an axial load of 100 newtons. Find the deflection in the spring and the maximum shearing stress in the material. Modulus of rigidity is 80 gigapascals. GPa means gigapascals. So every detail is given here. The small diameter, small d, okay, is 5 millimeters. It is given, and what else is given? Capital D is given 50, and number of turns 12. Load is given 100 newtons. So from this you will get the radius of coil 25 millimeters, and C is 80 gigapascals. So you convert that into megapascals. 80 into 10 cube megapascals or Newton per millimeter square. Okay, 1 megapascal is 1 Newton per mm square. So you can now find delta, the deflection, by substituting the values. All the values are known here. W is known, R is known, N is known, number of turns, C, the rigidity modulus, D, small d, the wire diameter. All the values are given, known. So we can find the deflection delta. Okay. So this delta we can directly calculate by substituting this. Okay. And maximum shearing stress we require now. Okay. Maximum shearing stress is found by this relation. Okay. So pi d cube by 16 into tau, this is the shear stress, is equal to W into R. So here all the details are known. We can calculate the shear stress tau from this equation. Okay. Let us see another example. A closed coiled helical spring is required to absorb 2.25 into 10 cube joules of energy. Determine the diameter of the wire the mean diameter of the spring and the number of coils necessary if the maximum stress is not to exceed 400 mega Newton per meter square. Mega Newton per meter square is nothing but megapascal, because Newton per meter square is Pascal. 1 Pascal is 1 Newton per meter square. So 1 megapascal means 1 Newton per mm square. Okay. So the maximum shear stress is not to exceed 400 megapascals. The maximum compression of the spring is limited to 250 millimeters. That is delta. Okay. The mean diameter of the spring can be assumed to be 8 times that of the wire. Mean coil diameter is 8 times that of the wire diameter, and the rigidity modulus for the material of the spring is 70 giganewton per meter square or gigapascals. Okay. So here the work done is stored as energy. Okay. Work done is stored as energy. So the energy to be absorbed is given 2.25 into 10 cube joules. Okay. So energy to be absorbed is equated to the work done, because work done is stored as energy in any material. So work done is given by the expression half W into delta, that is average load multiplied by delta. Assuming that the load is gradually applied, the work done is given as average load multiplied by delta. W by 2 is average load and multiplied by the displacement delta. Okay. And that is equal to energy stored or energy absorbed by the material, 2.25 into 10 cube joules, Newton meters. So W is calculated from this. W is calculated from this because delta is given 250 millimeters. Delta is given, isn't it? Yeah, delta is mentioned here, 250 millimeters. So taking delta as 250, let us convert that into meters into 10 power minus 3 equal to 2.25 into 10 cube. This is in Newton meters. Joules means Newton meters. So we convert this also into newtons. Meters, sorry. Delta into meters. So W is equal to, what is W from this? 2.25 into 10 cube divided by 250 into 10 power minus 3. Okay. So 250 into 10 power minus 3, or this is nothing but 4 in the numerator, isn't it? 4 or 8. 8 in the numerator. So W by 2 here. W by 2 is equal to this one. So 2.25 into 10 cube. And this is 0.25. 250 into 10 power minus 3 is 0.25. Okay. So this comes out to be 9 into 10 cube into 2. W. This 2 is taken to the right hand side. So it is 18,000 newtons 18,000 newtons or 18 kilonewtons. The load from this expression is obtained as 18 kilonewtons. This is work done, W into delta by 2. Okay, and W is obtained as 18 kilonewtons. And what else you have to find out? The maximum stress is not to exceed. Determine the diameter of the wire. We have to find the diameter of the wire and diameter of the coil using these conditions. Okay, maximum stress is not to exceed 400 mm square, Newton per mm square, and the maximum compression is limited to 250 mm, and the mean diameter of the spring is given to be 8 times that of the wire diameter. So maximum stress limitation is given 400 Newton per mm square. That we will use here. Okay, this is the expression we are using. In this, this can be written in this form: 2WR by pi r cube. This d cube is taken as 2r cube. Okay, 2r cube. So it becomes 8r cube. Replacing d cube by 2r, it becomes 8r cube. So this is 2 times. So 2WR by pi r cube. Tau is 2WR by pi r cube. That is equal to tau. Mega Newton per meter square. And we know the relation between these two. Mean coil radius is 8 times that of the wire radius. Okay. So using that, we'll get, substituting this value here, replacing capital R by 8r, small r, we can find radius of wire, okay, as 15.1 millimeters. 15.1 millimeters. Okay, from this. So W we have calculated 2W, R is 8R, and tau is 400 into 10 power 6. Actually 400 Newton, this is substituted in newtons, W. So this will be taken as 400 only, Newton per mm square. Mega Newton is nothing but 10 power 6 Newton. And meter square is 10 power 6 mm square. So mega Newton per meter square is nothing but Newton per mm square. So you can take 400 here, so that you will get R value directly in millimeters. This is given, okay, 250. Okay. So the small radius means, small r means radius of wire, and capital R will be 8 times of that. 8 times of that. Okay. So it is to be rounded off to the nearest, so that these conditions are not violated again. Okay. What are the conditions here? We have delta is limited to 250 mm and shear stress is limited to 400 Newton per mm square. Okay. Now that is about the spring, close coiled spring subjected to axial force. Axial force. Now let us consider the case of axial force W, and here axial twist. Axial twist. A couple. Okay. As shown in this figure, spring is subjected to axial twist. Yeah. The notation is same. Small d, capital D, that is, they are the diameters. Capital R is radius. coil radius, and n is the number of coils, and c is modulus of rigidity. So here what happens when the twisting moment is applied, axial twist is applied, is if it is applied outwards, the number of coils, they try to open up, okay, the number of coils will change, okay, they may increase or decrease, okay. So the number of spring coils will tend to increase or decrease depending on the sense of the moment, direction of the moment, okay. And if the number of turns tend to increase, then the mean radius of the spring coil will decrease, because number of turns, if it is increasing, number of turns is increasing, n here, number of turns means n. What happens to mean radius? It has to decrease because the length of spring remains same, okay. So mean radius of the spring coil will decrease. So let us now assume that the number of coils increases from n to n dash, and mean radius decreases from r to r dash, okay, understand? So number of turns are increasing and hence the radius of coil decreasing, okay. So in both the cases the length should be same. What is the length? 2 pi r into n, 2 pi r into n, number of turns, okay. When subjected to twisting moment, axial twist, so radius is now r dash and number of coils is n dash. So the length is 2 pi r dash n dash. And what is the curvature? In case 1, the curvature is 1 by r. Initially the curvature is 1 by r, so it is 2 pi n by l from this equation, okay. Similarly, after axial twist is applied, the curvature is curvature of the coil 1 by r dash is 2 pi n dash by l, 2 pi n dash by l, okay. Now from bending equation here, m by I is equal to E into change of curvature. We know that relation, m by I equal to E by R, isn't it? M by I equal to E by R. So E into change in curvature 1 by R dash minus 1 by R, that is E into 2 pi n dash by L minus 2 pi n by L. Taking 2 pi by L common, you will have 2 pi E by L into n dash minus n, or 2 pi into n dash minus n is equal to ml by ei, ml by ei, and that is the angle of bend. Total angle of bend is 2 pi into n dash minus n, 2 pi into n dash minus n, okay. So this is the relation we have now from this equation. Here this is nothing but phi, the total angle of bend, okay, and the derivative of this d phi by dl is equal to m by ei, m by ei, okay. And now total strain energy stored in this case is half into m into phi, okay, angular displacement, okay. In case of axial force, we have extension of the spring delta. Here angular displacement takes place, that is phi, okay. the total angle of phi is the total angle of bend is here phi n, no? That is half into that is average moment into angle of bend, that gives the strain energy stored. In case of axial force, it is half W average load into displacement delta extension. Here average moment multiplied by angle, okay, phi, that is the angle of bend. So when it is subjected to axial twist M, so these are the expressions we arrive at. We need to remember, okay. Let us consider one more example on this. A closed coiled helical spring is made up of 10 mm diameter steel wire having 10 coils with 80 mm mean diameter. If the spring is subjected to an axial twist of 10 kN mm, determine the bending stress and increase in the number of turns. Take E Young's modulus as 200 GPa, okay, 200 gigapascals. So what is the data given here? So diameter of wire is given 10 millimeters and having 10 coils initially, and mean diameter of coil 80 millimeters, and twist, axial twist 10 kN mm, and Young's modulus is given 200 gigapascals or 2 into 10 power 5 megapascals or Newton per mm square. 2 into 10 power 5 megapascals. So this is the data given, and what you have to find? Bending stress sigma and the increase in the number of turns. Increase in the number of turns. Okay. So here the bending stress is calculated by using bending equation. So the moment of inertia of the wire is pi by 64 d power 4, small d here 10 power 4, so which comes out to be 490.9 mm power 4. So the bending stress from the equation is given as m by I into y. Here m is axial twist bending, that is the moment, okay, 10 into 10 cube Newton mm, 10 into 10 cube 10 kilonewton mm it is given, so 10 into 10 cube Newton millimeters, and I value y in millimeters. Y is extreme fiber distance, that is diameter of wire is 10 mm, so extreme fiber distance is d by 2, small d by 2. So from which you will be getting the bending stress in the wire material is 101.9 Newton per mm square, and increase in the number of turns. Increase in the number of turns. So the length of spring wire is given as 2 pi r n, because initially the number of turns is 10 and the radius, mean radius is 40. Okay, you will get the length of the wire. So n minus n dash, the change or increase in the number of turns is given as this one. Okay. 2 pi n dash minus n is ml by ei. So we want n dash minus n, isn't it? So ml by ei divided by 2 pi. So substituting the values m, l, e, I, you will get n minus n dash or n dash minus n in this case as 0.04. So increase in the number of turns is 0.04. So after axial twist, the number of turns will be 10.04. N plus 0.04. N dash is equal to N plus 0.04. N is 10. So the number of turns increases to 10.04. Very small change occurs due to the given moment. Okay, we will discuss some more topics in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.